Hi everyone, in this video we'll take a look at hypothesis tests for a population mean. This is section 10.3 in our textbook. These are the slides for chapter 10 in section 10.3, and the slides have some good background notes and some good examples, and if you get a chance I'd encourage you to take a look at the slides. But for this video I'm going to go over some notes that I wrote separately. And we'll start with some background on this kind of a test. So again, these are hypothesis tests for a population mean. In the last section, those were hypothesis tests for population proportions. So the big difference here is that these are all involving a mean. And these kinds of tests are called t-tests. There are a number of ways to test a hypothesis about a population mean. If a population is normally distributed, or if the sample size is more than 30, and if the sample size is less than 5% of the population size, and this is the most important thing, if the population standard deviation is unknown, then the best kind of hypothesis test that you would want to do is the t-test, which is a test that involves a distribution called Student's t-distribution. Student's t-distribution is a symmetrical distribution. It looks similar to a normal probability distribution. It looks like this. The mean of this distribution is 0, so 0 is in the middle, and the values on the horizontal axis are t-values, and the test statistic, some t-value, can be calculated using this formula. The t-distribution is approximately normal, or bell-shaped, if one of the following is true. So either the population on which it's based is normally distributed, or the sample size is large. In other words, n is more than 30. If one of those is true, then the t-distribution becomes approximately normal. So again, in section 10.3, the hypothesis test that you will come across will meet these conditions. And for this reason, because they meet these conditions, and importantly because in these problems the population standard deviation is unknown, you will be using this kind of a test, the t-test. We'll go right to some of the examples. The first example is on a hypothesis test involving a population mean. It's similar to section 10.3, exercises 13 to 18, and also 21 to 24. Last year, patients visiting Half Moon Urgent Care waited on average for 24.8 minutes before being called in to see a physician. This year, in an effort to reduce the wait time for patients, the staff at Half Moon Urgent Care has implemented a new check-in and screening system for patients. After implementing this new system, the staff at Half Moon Urgent Care measured the wait times of 36 randomly selected patient visits and calculated the sample mean wait time to be 23.6 minutes with a sample standard deviation of 3.5 minutes. Is there sufficient evidence to conclude that the new check-in and screening system was effective in reducing the mean wait time for patients? Use an alpha of 0.10 level of significance. Note also that a histogram of the data indicates that patient wait times have a skewed left distribution. To start, at step 0, we'll summarize the information and identify the point estimate. This hypothesis and this study are comparing two different wait times. The wait time under the old check-in system, which was 24.8 minutes, and the wait time under the new check-in system. The population mean wait time under this new system is not known, but they did do a study. took a study and sampled 36 patients, observed their wait times, and calculated the sample mean to be 23.6 minutes, and the sample standard deviation to be 3.5 minutes. Based on that result, we could see that the sample mean wait time under the new check-in system, 23.6 minutes, is lower than the mean wait time under the old check-in system, 24.8 minutes. This seems to indicate that the new check-in system is working. It really is reducing the mean wait time for patients. However, we will need to test whether the sample mean wait time under the new check-in system, this 23.6, is significantly lower and therefore sufficient to conclude that the mean wait time really has been reduced. Our first step is to state the hypotheses. This hypothesis is involving a population mean, and for that reason, now we'll use the symbol mu. In particular, mu is going to represent the unknown of this hypothesis test, and the unknown is the population mean wait time for patients under this new check-in system. So here are the hypotheses using symbols. The null hypothesis is that the mean wait time for patients with the new check-in system is just the same as the mean wait time under the old check-in system. Remember that the null hypothesis is always the hypothesis of no difference. The alternative hypothesis is that the mean wait time under the new check-in system is less than the mean wait time under the old check-in system. So this hypothesis would be saying that the new system is reducing the wait times. And like the last set of notes, I have also written out these hypotheses in sentences. When you write these hypotheses on a quiz or test, or even in your own research, you don't necessarily have to write full sentences. Normally you would just write your hypothesis in symbols. But I've written it in sentences here just for full clarity. The second step is to verify the requirements for this hypothesis test. The requirements for this test are, number one, the sample must be a random sample. Number two, students' t-distribution must be approximately normal. And this will be true if one of these is true. If the population on which the hypothesis is based is normally distributed, or if the sample size is large, in particular if the sample size is more than 30. And then the third requirement is that the trials must be, in effect, independent. And this will be true as long as the sample size is less than 5% of the population size. So let's check these requirements. The first requirement, that is satisfied. In the description of this study, they mentioned that patient visits were randomly selected, so this is a random sample. The second thing is to check the normality condition. In the description of this test, it does mention that patient wait times have a skewed left distribution. In other words, the population of wait times is not normally distributed. But that's okay, because in this second requirement, either one of these can be true. So in this case, this is not true. The population is not normal, but we do have a pretty large sample size. The sample size is 36, that's more than 30, and so we're satisfying that condition. The third requirement is checking to see that the sample size is less than 5% of the population size. We don't know the population size of all patients who visit Half Moon Urgent Care, but we could plug in 36 for the sample size and then solve for capital N. So I'll put in 36 for sample size, solve for capital N, divide both sides by 0.05, and then we end up with this, that 720 is less than or equal to N. What this means is that this is true. Sample size is less than 5% of the population size, as long as the population size of all patient visits to Half Moon Urgent Care is greater than 720. And since this urgent care sees many patients each day, it seems pretty reasonable to conclude that the population of all of their patient visits is more than 720. And therefore, this is true, that the sample size is less than 5% of the population size, and therefore we can conclude that each trial is in effect independent. Alright, in the next video we'll finish this example and move on to some other examples.